in our field, and everyone is welcome to suggest names for future talks in that direction, with talks that are in fields that are related to ours or even a bit further away. So we've decided to have a number of talks from institutes that we have close to our own, that are working in other areas and doing excellent research there. For the first one, we didn't have to go very far. Turns out in the same building, there is an institute that has Maria de Maestro, 5-year seed grants, and they're doing science between chemics and physics. It's related to ours, but that I personally know very little about. So we found the director of the institute, Professor Eugenio Coronado, willing to tell us about what they're doing, why they're doing it, and what applications we might expect in the near future. So please go ahead. Thanks for coming.
Okay, thank you. Gracias por la invitación. Then, well, it's always a pleasure to give a talk at the IFIC. I did give one 3 years ago already, and every 3 years I can give one talk. Then, the idea today is to show a little our way of doing the research also in the institute that is in between chemistry, physics, and engineering also. But is when there are some physical aspects that are of interest also for you, and some applications that can be also of interest. There is some chemistry, but I will not show the chemistry. It is not at this moment so interesting for you. Then, in my case, you see the institute, the objective is to develop molecular science. And molecular science means now also molecular nanoscience. Then molecular nanoscience means to play with molecules at the nanoscale, to be able to control the molecules, where would you put the molecules, to be able to interrogate the molecules, one single molecule, for example, and to make devices based on these molecules. These are the objectives of the institute. That is a kind of institute of material science, but focused on molecules. This is the only institute in Spain of this kind, because all the institutes doing material science in Spain are general institutes in which you have a small part about molecules. But in our case, all the institute is doing, from different perspectives, research on material science, playing with different kinds of molecules. Not only one type of molecule, but in some institutes you have expertise in people doing electronics with the molecules. In other places, people doing chemistry with the molecules, chemical materials with molecules. In other ones, magnetism with molecules. In our case, we have all these possibilities together. Today I will not explain all these possibilities. I will focus more in the field that is more related with my expertise, that is more the magnetic molecules. But in any case, you will show the methodology, and you will see also the way in which we approach the research. That is a kind of research in material science. Then that's why I put that from molecules we can go to materials and then to devices, or from molecules and materials we can go to devices. Or the other possibility of title is from chemistry we can go to physics and engineering. This is the way. This is the approach we are following. Then we start with the chemical design of systems. We start with our molecules and our materials based on these molecules, and then the first step is the chemical design of these molecules that are of interest. Because they have a functionality, they can have electronic functionality, magnetic functionality, optical functionality, then you can have different functionalities, and then these molecules, we design them, then in the second step, we try to assemble them and organize them in a way, in a surface, or as also self-assembled materials. Then this is the second step, and then afterwards, we study the properties and the physical properties and also chemical properties, but mainly the physical properties of the system. And we develop in the institute, we have a part of people doing theory in which we try to model the properties we are observing. That means magnetic properties, that mean also optical properties mainly. These two aspects are the aspects that we are studying also, and also electrical properties. Then this is this step, the third step, and the final step is to develop once you have done all this kind of procedure, you can go to try to develop some applications, and then after with, in view of these properties and the limitations in the application, we develop again the chemical design to improve our system, and we continue this kind of circle. Then it's a kind of circle that is the typical circle of material science. Okay? But the originality is that is with molecules and not only with any kind of classical material. That is the other possibility. Okay, then you see applications that we are looking for is, for example, in molecular electronics and optoelectronics, then in which we are able to make systems that are luminescent and can be used for screens or lighting, and then there are some relationships with some companies. Mainly this is the people that are working in this topic is mainly Henk Bolling and Enrique Ortiz. These are the two groups that are working on more in these aspects. After there is another aspect that is molecular spintronics, in which is molecular electronics, but in which you introduce also the spin of the electron. You take advantage of that the electron is not only a charge, but also has a spin. And having also the spin, you develop materials and you develop devices that are much more efficient than the ones that you can develop with molecular electronics, and that has lower consumption in energy, for example, if you use the spin. Then the molecular spintronics is an area that is the most strong area in nanomagnetism, but the originality is that you add molecules and not only systems. That so far the systems people have been working with has been semiconductors or metals, magnetic metals, for example, and non-magnetic metals, but always metal and semiconductors are the typical materials. But playing with molecules is one new thing, if you want, and then we are developing this area in the institute, and also we are the leaders in Europe in this topic. We are coordinating several projects on this topic, including ACOS. Well, there are several things that we can do on this part that we are quite competitive. And then playing with molecules, I will show you that it's possible also. There are some people in the institute that are working in some molecules that can be used in quantum computing. That is one of the things that now also is promoted by the European Union. And then finally, there are other kind of materials, more for chemical applications, in which you can make molecular storage of some molecules, CO2 or this kind of molecules, separation of CO2 from nitrogen, and sensing of this kind of gases on surfaces, and also we develop some biomedicine. Then, but I will talk today about these parts, more about the parts dealing with the electronic part, if you want, electronic, optoelectronic, and magnetoelectronic, if you want. Then, for that, we have several kinds of molecules: magnetic molecules, luminescent molecules, electroactive molecules, bioactive molecules. Today I will focus mainly on the magnetic molecules to have a clear focus. Then, from this point of view, if you play with molecules, there is an area that is called molecular magnetism that started in the 80s. And then this area is developing and finding interaction with other areas, and the other areas are the area of nanomagnetism and the area of, that is with molecules, and the area of materials based on molecular systems. Then in the nanomagnetism area, there are two topics that are important. Quantum technologies, that is a big area at this moment, that is increasing, and the other one is molecular spintronics, as I told you before. And in the materials part, aspects, one important topic also is 2D materials, graphene-like materials, then in which molecular magnetism can also give some input, and also the area of MOFs that are lattices that are porous lattices, if you want the zeolites. The zeolites are porous materials but made with silicates or aluminosilicates. Then here, instead of using silicates or aluminosilicates, you use organic and inorganic stuff. It's a metal-organic framework. You have a metallic part and organic part, and then you have more flexibility. And then there is one hot topic now in chemistry, because this kind of topic can have a lot of applications in catalysis and other kind of separation of gases, everything. But also in magnetism, MOFs can also be useful in magnetism. Then today I will show you some results of quantum technologies, some results about molecular spintronics, and some results about 2D materials. This is the objective today. Then, okay, I will start with quantum technologies. This, you know that in May this year, we have had a new flagship in Europe that is on quantum technologies. This flagship has a lot of money if you want, but it's difficult to enter in this flagship. It's not so easy for people doing materials to enter. For people doing more algorithms and computing with that, well, without materials, it's more easy to enter in this part. But well, for the materials people, it's more difficult. But in any case, and it's even more difficult to enter with molecules. We propose that with molecules we are going to solve some problem here. People are not believing us. Then from this point of view, they are very skeptical. As well, in this case, well, they call that the quantum second revolution, and then molecules is one of the things that well, we try to put our input here with some molecules, and also, okay, chemistry. Chemistry is out of all this kind of topics so far. Then, but we are trying to enter in this kind of topic, playing with molecules and doing some chemistry for designing these molecules. Then there are several people in the group working on this topic. Then these are here the names. Well, Alejandro Gaita is the person also that is more leading this part, because he has also an ERC for doing this developing this kind of topic, and a consolidator grant. And then, okay, I will, for explaining that, first I will try to show you which are the materials with the molecules we are using. The molecules we are using is what we call molecular nanomagnets or single molecule magnets. Then these molecules are molecules that are simply fragments of metal oxides. Then you have here manganese, for example, and here you have an oxygen group, and then this is a metal oxide. But if you put in the periphery, you put some capping ligands, some molecules that cut the growing of your system, you end up with a molecule of nanometric size that has some properties related with the oxides, but is an oxide at the molecular level. Then this kind of molecule has some manganese, and then these manganese are coupled magnetically, and at the end you have, due to this coupling between the spins in this molecule of 12 manganese, then you have a ground state that has a spin equal 10. Then the ground spin state of the system, once you have all the exchange interactions between the ions, is spin equal 10. But this system is a kind of disc-shaped system, has some axial anisotropy, and due to this anisotropy, the spin is splitting at zero field. You have a zero field splitting, magnetic anisotropy, in such a way that the ground state, the projection of the spin plus 10 minus 10 is the ground state, and the plus minus 0 is the most excited state. And then you have plus minus 9, 8, 7, etc. until reaching 0. Then if you want, the idea of this kind of molecules is to prepare a kind of magnet with memory. And the way to do that is to have this kind of a scheme, because in this scheme is not so difficult to understand that if you want to pass from the spin with projection plus 10 to the spin to projection minus 10, that is are the two poles of a magnet, if you want, you should overcome this barrier. You should have all the projections. The spin should start in this direction, has in a quantized state the other projections, but should go hopping from here to here to here, and then at the end you go here. Then that means that for going from this orientation to this orientation, you should overcome a barrier, a super paramagnetic barrier. Then this problem, this situation, if you have a big barrier, the barrier is much higher than the room temperature energy. In that case, you will have a magnet that will have memory at room temperature. The problem is that this barrier is not so high. This barrier is 100 or less, 60 wave numbers, 100 wave numbers maximum, and then that means that this kind of energy at above 4 Kelvin, the system is going over the barrier thermally. Then you have the system only behave as a magnet below a given temperature. But it's nice because, well, you have this possibility that is quite nice. The other possibility is that also this is a quantum object. Then, due to this quantum object, you can also have quantum tunneling from here, from ms plus 10 to minus 10, without overcoming the barrier. Then this process is also in competition with the other one. It depends of how these wave functions that are here are mixed between them in a quantum way. Then, if you have a mixture, then in that case you can have a very sharp relaxation, and then the system is not having memory, because very quickly the system has not this barrier. Then you can have the two situations. Then chemically, the chemists are trying to, on the one hand, to try to have barriers as big as possible, to have classical memories, magnetic memories, but of the size of 1 nanometer, because that measures 1 nanometer. But there are other chemists or other physicists that are trying to maximize this part, because if you have a mixer between these two parts, a mixer is good for having a good qubit for quantum computing, because for that you need to have the two states. That a qubit is only a system with two states, but these two states you should have a mixer between them. If they are disconnected, these two states, the qubit is not good. Then you need to have the mixer. Then for quantum computing you need this one to be big. For classical computing, for memories, classical memories, you need this one to be big and this one zero. Then you play with these two processes, and then is the way to do that. Then you see these are, well, these systems appears in '93 already, and then the systems show, as I told you, at low temperature hysteresis. Then this is magnetization as a function of the magnetic field, and you see that you have hysteresis, but hysteresis has some steps, and these steps is due to the quantum tunneling effects, because there are some quantum tunneling, even small. You have a quantum tunneling effect not only between this state and this state, but also you have quantum tunneling when you apply a magnetic field. Some states, this state will enter in resonance with this one, because this one will increase in energy, this one will increase in energy. At the end, you will have some resonant states, and in these resonant states, you will have a fast relaxation. And then if you have no resonant state, you have no tunneling here. Here you have tunneling again, no tunneling. Then you pass from situations of tunneling and not tunneling. That's why you see these steps. But well, the message is that you have systems in which you can have memory. Then you have molecules. Then so far the system with memory, the magnetic memory, were in domains, in bulk systems. But this is you obtain the same phenomenon with a single molecule. With a single molecule, you are able to observe this kind of behavior. Then this is quite nice. That was quite nice, and then the reason was an isotropic spin in your system and a high magnetic moment. Then this is the reason why you have this kind of situation. An isotropic S, and also the spin and big S. An isotropic and big S. These are the two conditions. Then, okay, thinking a little, which are the systems that exhibit high anisotropy in the periodic table? The rare earths. That has a strong orbital contribution to the magnetic moment. Then in that case, if you pass from D metals to F metals with rare earth, you don't need to have 12 centers to have this behavior, to have a big spin. With one single atom that can be a lanthanide atom, in a coordination that can be with organic ligand like this one, or with an inorganic cluster like this one, and then you have your lanthanide trapped in a molecule, that is this kind of molecule or this kind of molecule, then this lanthanide exhibits a big anisotropic. Now it's not S the spin, because the spin is not a quantum number, it's the sum of L and S, is the total angular momentum, and then the total, you have a total angular momentum quite big in this case, and it's also anisotropic due to the crystal field that you are having here. In this case, the crystal field is an anti-prismatic crystal field, that is quite nice. It's an axial crystal field, like in this case also. Then, with this kind of situation, you have exactly the same behavior as here, but only with one single atom. This is the second generation of system. This is the first generation, if you want. And then with these systems, for example, I show you this kind of system. In this system, for example, what you have is the antisymmetric, the antiprism geometry. You have oxygens that is a kind of cube in which you have turned by 45 degrees one phase with respect to the phase below. And in that case, in the middle you have your lanthanide. And then this system is a system that, if you calculate with crystal field approaches, which is the ground state of this system, you discover that it's a system also that has also a barrier that similar to the case of manganese 12. Then, for example, in the holmium case, the holmium case, the spin is 2, the L is 6, the term is L plus S, the J term is 8. Then in that case, what you have is, due to the spin-orbit coupling, you have this splitting, because the spin-orbit coupling is quite high. And then after the spin-orbit coupling, you have a splitting due to the crystal field. This is different from the case of transition metal ions, transition metal ions, in which the crystal field is much higher than the spin-orbit coupling. Now the spin-orbit coupling is much bigger as term, like the much more than the crystal field splitting. But okay, then you have this kind of situation with this scheme of levels that is similar to the one which you saw before with manganese 12. This is the important thing. The ground state, for example, here is Mj, for example, for this system with this geometry, with antiprismatic geometry. The Mj, if you calculate, is Mj plus minus 4. And then, okay, you have the Mj0 is here. Then if you want to go to plus 4 to minus 4, then you should pass and overcome a barrier. Then you have, again, your barrier. Then this system, again, is a single molecule magnet, but now with one single atom. Then we have improved a little the system a lot, reducing the system because this is much more simple. In the other case, to control the exchange interactions is not so easy, chemically or structurally, because we don't control the structure of a system when we construct our molecule. But in this case, to control the coordination around the lanthanide is much more easy, because it's one lanthanide, you put here a ligand, and the ligand, very easy, you can predict which will be, from the ligand you start with, you can predict which will be the coordination. Then this is much more easy to produce and much more easy to design systems. That is one important thing. Then but you have this barrier. Then the system is a single molecule magnet, but also you can have quantum tunneling. And this system is an object, much more quantum object than an object with a lot of spins. If you have a lot of spins, the system is more classical. This one is more quantum system because you have purely a system with very few amount of levels and then not a lot of excited levels that can be mixed with the ground state. Then, okay, then this representation I can do here again as a function of the Mj. Then here, if I do that, you see the barrier, but you see the barrier is around 300 wave numbers. That is quite high, higher than in the case of manganese 12. The manganese 12, I told you, that was 100 maximum. Here, you can have barriers of 300, 3000, then it's very easy to increase the barrier with lanthanides. Then you expect to have memories at room temperature, but the situation is no. You have no memories at room temperature because always the system is quantum, the nature of the system is a quantum system, and in that case you have always tunneling. Tunneling, you cannot avoid to have tunneling. There is always some term in the Hamiltonian that makes these two functions in such a way that you have tunneling. It's impossible to have, well, impossible so far. Playing with any kind of symmetry has been impossible to have very pure functions here and here and to have the system without tunneling. Always you have tunneling, and then, for example, you see you expect here to have a barrier of 300 wave numbers, but experimentally, if you measure the barrier, but you can measure with magnetic properties, the barrier is 2.5. Why is so low? Because you have a lot of tunneling. These two states are strongly mixed. Then this is good, I told you, for quantum for having a good qubit, because for qubit you need to have a strong connection between the two levels that are in the ground state. Then you see you can also demonstrate that you have not memory, because in the magnetization you see a hysteresis loop, but here at zero field you have no hysteresis, indicating that at zero field what you have is a fast tunneling from here to here. That is what you have. Then can we use this kind of system for quantum computing? What we need for a quantum computing system? The basics of quantum computing is a qubit, to have a qubit. And here we can have a qubit. For having a qubit, you need to have two states. Two states that can be connected through electromagnetic radiation. Then, for example, with microwaves, you can pass from one state to the other, and you can modulate, well, you can have different orientations of your, well, different mixtures of your two states. And then you have not 0 and 1 now, but in quantum systems you have a combination of the zeros and the ones, a linear combination without any problem. That's why the quantum computing is different from the classical computing, because you have this possibility. You can, in that case, modify in a continuous way the orientation of your spin in these systems. But for that, well, with a spin you can do that, because in a spin you have always two states. In the doublet, in the ground doublet is two-state system. Then here you need two well-defined states with high quantum coherence. This is the problem. To have high quantum coherence with the spins is not so easy. The spins are very strongly interacting with the surroundings, the magnetic noise that create the other spins with Doppler interactions, for example, or hyperfine interactions. Then having this kind of problem, what you need to do is, for having high coherence, you need to have at T2, a relaxation time of the spin. The direct relaxation time is T1, that is direct relaxation, and the one that is more related with coherence is T2 time, that in NMR people are using. Then this T2 time should be as high as possible for having time to perform an operation with these qubits before the qubit disappear of the state in which it should be. Then you need time. The time you need is not so long. You need, as time you need microseconds. If you have of the order of microseconds, is enough for addressing your spins and to perform some operations. Well, of the order of 100 microseconds, not 1 microsecond. 1 microsecond is not good enough so far. And also, well, the third problem you need is you need to integrate in a scalable architecture, because you should address spin by spin or qubit by qubit your system. Otherwise, it's not working as a quantum computer. You cannot put the system completely random in a solid. Then you should put in a controlled way, in a scalable fashion. Then this is difficult to make with these systems some computer, some quantum computer. But in any case, to start with, what you need to do now is to maximize that. And also, if you play with molecules, at least you can have technological nanotechnology to put your molecule where you want with a nanometric precision. Then can be in the future can have a scalable architecture. Then much better than to take silicon. The approach now people are doing, the physicists, if you want, is to take silicon, and then in the silicon you dope with phosphorus. Then silicon is not magnetic, you add some phosphorus. This is the spin that is there, but this spin is diluted. You can add 1 atom of phosphorus in one surface of silicon. In that case, you have not the coherence. The coherence time is very, very high. Then the system is very coherent. But the problem is that it's random. And also, you cannot play with more concentrated systems. If you concentrate your system with phosphorus, in that case, very quickly you stop your coherence. Okay? Then there are problems in solid state physics that, well, with molecules can be also problematic, but you can have another approach. Okay, then you need, for playing with the spins, you need a spin doublet, and also, as I told you, isolated and decoupled from the surroundings. In such a way, the surroundings are generating magnetic noise. Electronic and nuclear spins are generating magnetic noise around your qubit, if you want, but you have also, in your solid state, you have phonons, and the phonons also at high temperature are also creating noise. Then you have problems with phonons, you have problems with the spins around. Then you should minimize the phonons and this effect, also this effect. And then we are working in these topics to try to minimize that. I will show you now, as an example, how we can decouple the spin from the surroundings using approaches that are not so conventional. The simple one is to dilute the system. As I told you, you put a spin only. If you dilute, you avoid to have the magnetic noise. You have no magnetic noise because the dipole interactions between your spin qubit are zero. But you should invent more clever things, otherwise, if the two spins are like that, and for having a computer you need a communication between the spins, otherwise you cannot have a Q-gate, that is what is determining a kind of operation or algorithm that you should do. Then if you have two spins that are separated, you cannot operate with them. Then a qubit alone is useless. You need two qubits together, or more than 2, or 3, 4, 5 qubits together, but all this is creating the coherence if you are not making some solution. Then I will show you that it's possible to make some solution for approaching the qubits without increasing the coherence. This is what I will show you now. Then you see, you have a qubit, a central qubit. This central qubit is interacting with other spins that are around and protons that, well, nuclear spins. This is electronic spins in blue, with this spin that is the central qubit, and with protons that are nuclear spins. Then hyperfine interactions and dipole interactions are destroying your coherence. Then how you minimize dipole interactions? Okay, spin dilution. You dilute, and then there is no problem. You put only one spin in your solid, no problem. How you reduce hyperfine interactions? You avoid around your spin center any kind of atom having nuclear spins. For example, protons the hydrogen has a nuclear spin. Nitrogen has a nuclear spin. Then you should avoid to have nitrogens or protons, because otherwise the nitrogens and protons will interact in a hyperfine way with your spin that is here, and then you will have problems. Then nuclear spin-free molecules should be used. Then phonons, with phonons, I will not talk now, but I will focus on that. But with phonons, it's also possible to to improve. Knowing the vibrations of your molecules is also easy, well, it's not so easy, but it's possible to make some guidelines to improve also the coherence playing with phonons. But well, in any case, with that we have enough for today, with trying to make these kind of things. But okay, you see, nuclear spin-free molecules we can design chemically. Spin dilution we can do, no problem. But the problem is that with this approach, as I told you before, you cannot communicate 2 qubits. Then you need another approach that allows you to put 2 spins together without increasing this kind of decoherence. Well, the step now of people is not to maximize that. The people, what they are doing now is to try to study the coherence time as a function of temperature to see how the systems are good or bad. Then, for example, there are 2 systems in solid state, the silicon, as I told you, doped with phosphorus, or the NV centers of diamond. In diamond, you can also put some vacants, and these vacancies are NV centers in diamond. And in diamond, the T1 is triangles here, and also T2 is always below T1. And if you see in diamond, in the NV vacancies, these are quite good. And also, in the case of silicon, the triangles are T1, that are these ones here. No, should be the square. The T2 is what I like here. The T2, you see that with silicon above 10 Kelvin is not good for having quantum computing, because the silicon with phosphorus is having a very small decoherence here. You see that decrease. Then it's better the NV centers up to 100 Kelvin can be okay. But okay, people were playing with molecules, and they obtained with, for example, playing with simple molecules. For example, this molecule that is phthalocyanine molecule with copper here. You put a small amount of copper that was published not a long time ago, 3-4 years ago. Then you put an amount of copper here in this molecule, and then you put on a surface and you measure the coherence. And then with this, in this case, with copper, you see that you have the coherence times that are below the NV centers, but are not so bad. But you have nitrogens that is not so good. Then what we can do chemically? Remove nitrogen. Then people were removing nitrogens, making other molecules. For example, this one in which you have sulfur instead of nitrogens, and with this kind of molecules, they obtain for T2 this kind of behavior. Then now we are better, even better, than NV centers. Then with molecules, the first message is that it's possible to have coherence times that are higher than solid state physicists are doing with solid state systems. For example, with silicon doped with phosphorus or with NV centers. This is one message that can be good. But okay, with that, that not prevent you to improve your system, because what you need is to have 2 spins together in order to have big coherence without destroying the coherence when they are approaching. Then the way of doing that is to make a kind of protection around your qubit. Your qubit, well, to screen the magnetic field. Then you should invent a way in which your magnetic field, that magnetic noise that is around, is not affecting this nanomagnet that is here. Then you screen the magnetic field from outside. Put some barrier that screen the magnetic field. How you do that? Is in such a way, like make invisible your magnetic moment to the magnetic field. Okay, this is not so easy. Then because any kind of magnetic moment, any kind of spin, will have a Zeeman effect when you put in a magnetic field. Then, but we will try to do that in such a way that the Zeeman effect will be zero. In such a way that our system will not be sensible to all the magnetic noise. Then to do that, the way to do that is to play with the electronic structure of the system. You invent an electronic structure in such a way that you can improve this situation in such a way that you have a situation in which for a given condition, the magnetic field is not affecting your spin. Your spin is invisible to your magnetic field. Then I will show you that this can be done by having tunneling gaps as big as possible. Tunneling gaps means mixture between the known states. Tunneling gap means that this state and this state, tunneling gap is this kind of gap, and this kind of gap appears when there is a mixture between this state and this state. If there are no mixture, the tunneling gap is zero. Then you should maximize this tunneling gap, and maximizing the tunneling gap, you are able to make your system invisible to your spin is invisible to the magnetic field. Then why is that? Then you see, this is a normal spin system, that a normal Zeeman effect. That you have, in the Zeeman effect, you have the two states, and then you apply, you have here a doublet, you apply a magnetic field, and you have a Zeeman splitting here. But in some cases, instead of having this situation, you have an electronic structure having a tunneling gap, in which what you can have is a kind of state that is like that, another one like that, and due to the mixture between this state and this state, they have no mixture in the middle, because in that case they interact strongly when they cross, and they didn't cross, and they produce this function and this function, and here they produce a gap. And then, if you observe this kind of situation, this slope here is zero, this slope here is zero, then at this magnetic field, the Zeeman effect is zero. The derivative of this function with respect to this function that is the difference between this one and this one, and the magnetic field is zero. Then you have a Zeeman effect zero at this point. Then you are playing, in that case, with what we call atomic clock transitions. Then these atomic clock transitions are transitions that, if you want, are insensitive to the first order, to the magnetic field. In this position, you can have small fluctuations of your magnetic noise, but this system will have this transition very precise, because it is horizontal in an area. Then you are in this area, is the area, the less sensitive area to the magnetic field, zero. If you are in the maximum here and the minimum here. Then if you are in this area, the system is what we want, will be coherent. Even if around you have a lot of magnetic spins. Because the Zeeman effect will be zero, will be not affected by the magnetic system that are around. Then in this molecule that I showed you before, you can measure experimentally, and the Zeeman, this kind of tunneling splitting is 0.3 Kelvin, that is big compared with other systems. And then, well, I showed you before that these systems are having a strong mixture, that's why you have this kind of splitting and this kind of mixture. And then if you combine this kind of splitting with the nuclear spin of, you have a nuclear spin in your holmium system, the holmium system is 7 halves, then the 7 half nuclear spin is mixed with the MJ values, +4 -4, and then you generate not one doublet, but is one doublet split in 8 levels. Then if you apply now a magnetic field, you have this situation. Applying a magnetic field, you have, this is one state, the -4 and the state +4, but they are split due to the nuclear spin of the holmium. And then in this case, if there is a mixture between this state and this state, you will observe EPR transitions that are forbidden, because the selection rules tell that for going from here to here, for having a low transition, in APR is MJ0 ±1, here is ±8. Then here is 8 the difference. Then it's strongly forbidden. You should not observe anything except if you have mixture between the two states. And then when you measure, you observe. That means that there is a strong mixture between the two states. And then now, if you focus in this region you see that there are crossings between functions. And these crossings is where we should observe the clock transitions. You have crossings here. This function is crossing with this function. Here you have a crossing, another crossing. You have plenty of crossing here. And then if you focus in this region, you have plenty of crossing in this region. And then these crossings, due to the mixing, then you will have new functions that appear due to the mixing between the two initial functions. And then you will have here a maximum, here a minimum, maximum, minimum, maximum, minimum, maximum, minimum, 4 clock transitions. Then you will have 4 clock transitions. Then if you are in these fields that are quite small, 20 Gauss, for example, 20, well, the order of in millitesla, 20 millitesla, if you want, then here you have 20 or 70 or 100, then there are 4, you apply a magnetic field, and in these 4 magnetic fields, your system will be coherent, you can see here. Then if you are here at a magnetic field of 25 millitesla, that is just here, in the first clock transition, the system, the coherence time, T2, is diverged here and obtain values of 8 microseconds. Even if the system is concentrated, it's independent of the concentration. You can approach a lot the system, and then always you will have of the order of 8 microseconds, and you don't destroy the coherence thanks to this clock transition. Then the same with the 76 millitesla, that is this one, that also you have clock transitions, 137 and 178. Then you have 4 special magnetic fields, at which, if you apply this magnetic field, you are able to make operations with two spins because you don't destroy the coherence. Then this is a nice approach that we will publish in Nature last year, but it's a way to avoid, to overcome the problem of magnetic noise. You don't have magnetic noise if you are working in these clock transitions, and for that you need systems having this kind of structures with this kind of crossing of levels in the ground state. Okay? Then this is a message that, well, explain you that we are able to make qubits that can have high coherence enough, but also we can approach these qubits without destroying the coherence. If you compare now the normal manganese 12 that I have shown you at the beginning of, there are more cluster type systems. Here, you see the tunneling splitting, that is the key. Here is of the order of 10 to the minus 10 Kelvin. Here, or wave numbers that is more or less the same. But here, if you go to the erbium one or to the holmium one, and the holmium one I told you before is of the order of 0.3, 0.4 Kelvin, then here, you see, we are at least 9 orders of magnitude in tunneling splitting bigger. That's why these systems are quite good. The systems with mononuclear single molecule magnet with one lanthanide are much better for using, has very large tunneling gaps. Then these ones are very good for using as qubits, while these ones can be good for using as classical magnets. These are classical magnets because here you have always a barrier, and the tunneling barrier is very small. That means that the spin is not tunneling, but here the spin is strongly tunneling, and this one is much better for applications in qubits, in quantum computing. Okay, this is the first message. Second message, then that this is, well, I will talk to you now about quantum, about molecular spintronics. Then the first part was to show you that it's possible to make some kind of system that can be used as qubits based on molecules. That is what I have shown you before. Now I will show you that it's possible also to play with molecules to make some spintronic devices. Then in spintronics, usually people that were working on that were working with metals and semiconductors, magnetic and non-magnetic, some metal oxides also. But okay, it's also possible to take advantage that people were developing some strategies to develop electronics with molecules, and also molecular magnetism, because with that you can obtain some magnetic molecules as I have shown you before. Now, then in the intersection between these three areas appears now the molecular spintronic area. That is a new area in which, well, you can also develop things that are different from the ones you can develop in classical spintronics, because again, in spintronics the problem you have is that your electron should travel through a medium that can be a metal or a semiconductor, and you expect that your electron will keep the spin without losing the spin while he's traveling. Then you need for that high coherence times again. And for having high coherence, you need to have small hyperfine couplings, and also you need to have, well, in that case, T2 times as big as possible. Then when you play with molecules, it's much better, because with molecules you are not having strong spin orbit couplings in some cases, with organic molecules I mean, because you have carbon or you have systems like that. And with carbon or with light atoms, the spin orbit coupling is quite small, and the spin orbit coupling is destroying also the coherence of your spin. The spin is mixed with the orbit, and in that case you don't have an spin, you lose your spin very quickly in your system. Then the coherence time in a molecular system is much better than in an inorganic system. That's why people try to develop molecular spintronics, with the excuse that you can improve, in that case, the coherence of your spin. The problem is that your spin is traveling, but it's traveling very slow. Because in organic chemistry, your conductors or semiconductors, in principle, the semiconductors are very slow. They are not very fast. And in that case, you have a problem. Well, if you want to go from the bottom electrode to the top electrode, and you need to spend for that, I don't know, you should pass 10, 15 nanometers. Perhaps in 10, 15 nanometers, if the system is very slow, spend long time to do that, and the coherence time is lost, even if it is the distance is very small. because it's very slow. While in the inorganic systems, the system is much more faster, the coherence is smaller, but the speed is bigger, then you can compensate. But well, in any case, the physics of one part or the other, the parameters are not the same, and it's worth to examine if molecular systems can be useful. Then everybody use spintronic devices. For example, in the disk of your computers, the hard disk, the magnetic disk, then the head of the disk here is a sensor, a magnetic sensor that is a spintronic device. Then, and also for magnetic memories, you use also sometimes you take advantage of the spintronics to make your magnetic memories better, much more powerful. You want. Then in spintronics, what you have, the basis of spintronics is what we call spin valves. That it's possible to observe in spin valves diamagnetic resistance in magnetic multilayers. That is simply to put two magnets. You have here two magnets, and in the middle you put a non-magnetic metal. And then these two magnets can have the magnetic moments, so the magnet can be oriented parallel or anti-parallel fashion. And then, depending of this configuration or deconfiguration, the electrons that are going to pass from one electrode to the other can pass easily here with a small resistance, or if you reverse the polarization of the spins in this direction here in the electrode up and down, in that case the resistance is much higher. You have much more scattering, and then because when you inject, this is a spin injector, you inject the spins always in this direction, in this kind of spin collector system that is in the middle, that is non-magnetic. Then you inject the spins in this direction, and when the spins reach the other direction, cannot enter in the second electrode, and then, well, no, in that case can enter easily in the second electrode because they don't need to change the spin, then the resistance is small, while here the resistance is quite big. Then you observe a variation in the resistance that depends of the orientation of your spins that you are injecting. Then this is a strong magnetic sensor. Then with this kind of things, this is the basis of spintronics. Has this kind of difference in resistance that can be a giant magnetic resistance in the two configurations of your electrodes, or your magnetic electrodes. Then, how you measure that? You apply your magnetic field and you measure the resistance. Then first you magnetize your system negatively, for example, with the two spins in this direction. Then, in this orientation, the two spins are parallel. The resistance is small until, in a moment, one of the two electrodes is changing the orientation. The one that is soft, it's a soft magnet, change the orientation. This one is changing the orientation, while this one is a hard magnet that is staying in this orientation. Then, in that case, you have this situation anti-parallel, and you have a high resistance. And then, when you overcome when you continue and you overcome the coercive field of the second electrode turns in this direction, and in that case you pass again to a low resistance. Then you have a system with two states, low resistance state and high resistance state, and that can be quite high, quite sensitive to the orientation of your magnetization. Then you do it in this direction, and if you go back in the other direction, it's the same. You have the same curve in the other direction. Then you should observe, for having a spin valve, what we are going to measure is the resistance as a function of the magnetic field, and we should observe this kind of butterfly behavior that indicates that you have this situation. Then, in this case, in molecular spin valves, what we try to do is to change this kind of metal that is in the middle, or insulator that is inorganic insulator, by a molecular semiconductor. And then in this way, we can develop molecular spin valves. There are problems, is that the injection is not so effective from the inorganic world to the organic one, because there is a mismatch in the conductivity between this part, and this is a problem. And also, well, you have more problems, but what you need to do for improving this injection is to pay attention of the hybrid organic-inorganic interfaces that are here in the middle. Then the interface engineering is one of the things that in which a lot of people are trying to improve for making the system better. This is not only in spin valves, it's also in organic electronics in optoelectronics, for example. If you want to make an OLED device or a molecular, if you want solar cell, you also need to improve the interfaces to have good efficiencies. Then you need to improve the interfaces, the energy of the interfaces, and also the connection between the two parts. Then this is a general problem always when you try to construct any kind of device. Then, okay, this is important also in this area, but also if you play with semiconductors that can be also having some optical properties, can emit light, for example, then this semiconductor can be used as a spin collector and also as a system that emits light. Then you can make a multifunctional device. For example, one possibility is to make a spin OLED. A spin OLED means a system in which you can control the emission of light, or you can enhance the emission of light thanks to the spin polarization that you generate with two ferromagnetic electrodes. Then this is also a hot topic in this area. I will show you now one example that shows that it's possible to construct a spin polarized OLED, in which you can polarize the spin when entered inside this kind of semiconductor, and you can emit more light than normally. Then, well, this is one possibility. Then what I will show you is that in molecular spintronics there is this field that is to make a molecular spin OLED, but also you can take advantage and goes to molecular nanospintronics, because you can put here a semiconductor here or a nanoparticle, or at the end a molecule. Then you can also pass this area. Molecular spintronics is divided in molecular based spintronics and molecular nanospintronics. Then there are the two possibilities, and then this is really, well, this is the thickness of this layer is nano, is 10, 20 nanometers. That's why this is also nanometric from the point of view of the thickness. But you can also construct a device that is a nano device, in which the electrons are nano, and also the molecule you put in the middle is a nanomolecule. This is more challenging from the fabrication point of view, if you want. But well, the properties here are also more interesting from the quantum point of view. You have more quantum properties here than here. Okay? Then, in this case, molecular-based spintronics, I told you, I will put you an example that is the spin OLEDs. And here, I will show you also that it's possible to switch the magnetism playing with this kind of devices. We can control the spin of a single nanoparticle if you want. I will show you here that with this example. Not with molecules, not with a single molecule, with a nanoparticle made by molecules with 20 or 30 molecules together. Okay, then I will show you one spin OLED and molecular memories made with molecular nanospintronics. This is what I will show you now. Then in spin OLEDs, I told you that in spin OLEDs, what you have is your two ferromagnets in the middle of the semiconductor. You have an organic spin bulb, but at the same time, this organic semiconductor should emit light. Then it's a combination between this part and this part. Then for making that, an OLED has the same structure from the engineering point of view than organic spin bulb. The difference in an OLED is that the electrodes you are putting are not magnetic. Then if you change the non-magnetic electrodes here by magnetic electrodes here, in an OLED you can obtain a magnetic OLED. And perhaps this is a spin OLED or not, but this is not guaranteed. But what you need to do is at the end to have a spin polarized OLED in which you can, thanks to the polarization that you reach with the spin bulb effect, you can enhance.
What is the O for OLED?
Organic. Organic. OLED is organic, then that means organic light emitting diode. Okay, then usually people are playing with LEDs. The OLED is the organic. Then here you see organic spin bulb, organic LED. Then what you need to do is to try to put these two fields together, and then the aim is to control the electroluminescence via a magnetic field. Then you should control what we call the magnetoelectroluminescence effect. And there are several people in the group working on this topic, and I will show you some results. Then you see in an OLED what you have, for example, is a cathode that can be reactive, and an anode that, well, usually is ITO, that is not reactive, for example. And in that case, you have here your organic part that is a semiconductor that has an HOMO. This is the highest occupied molecular orbital, and a LUMO, that is the lowest unoccupied molecular orbital. Then you have a gap between the two, and then you inject electrons in the LUMO, that is an empty orbital, and you inject holes in the HOMO of your system. Okay? Then what you need to do is also to have a kind, the energy of the ITO and the energy of the HOMO should be close. The work function of the anode of the ITO, this kind of the ITO is indium tin oxide, that is a transparent oxide that is metallic. Okay? And then here you put a metal that is a reactive cathode, for example, barium, for example, and then that's why you should encapsulate the system sometimes. But well, in any case, you can also here have the energy, the work function of the metal should be close to the LUMO of the system to inject the electrons. Then you should have this kind of engineering of interfaces to have to be able to emit light with a voltage that is not so high. Because if this is not having this kind of configuration, you need big voltages to convince these holes to go here or these electrons to go here. Then this is the way in which you have this kind of system. You have an injection of charge here, electrons and holes. Then you form two types of excitons, because here this system will form an exciton, and this exciton is only the combination of the hole with the electron. And the excitons can be singlets, because, well, singlets and triplets. And the singlets are 25% and triplets 75%. And that means that the electroluminescence, that is fluorescence, is always due to that. You are losing this part. When you make an OLED device, you are losing the 75%. In the OLED device, in which this one is organic material. In the organic materials, you have fluorescence. Phosphorescence is more with metallic systems, with rare earths or other kind of metals, transition metals. But okay, then in that case, the idea is to change these statistics, to make here 25 of singlets is what you obtain, 75 of triplets, then you need to increase the amount of singlets. And how you can increase the amount of singlets? Then, if you have a spin valve and you put this configuration, you think that it's easy to understand that in this configuration you are enhancing the amount of singlets. This is a singlet. Okay? And while here you are enhancing the amount of triplets. Then, if you are in this configuration in the spin valve and you inject electron and holes with these configurations, in that case you will enhance the amount of singlets. And then instead of having 25%, we have more, and then in that case we have more luminescence. Then the idea is this one. Okay? Then there is a problem, is that the OLED operates at high voltages, above 2 volts, while the spin valve is only working at very low voltages, below 1 volt. Then you need, for making the two parts compatible, what you need is to decrease this one, that is quite difficult, to decrease the OLED below 2 volts, or better, to increase, in that case, the operation of the spin valve. And the operation of the spin valve, I will show you that playing with the interfaces is possible to increase up to 7 volts, and in that case, the system will work. Then you take this system, you use this kind of organic molecule, this ambipolar molecule, that means that the molecule can transport holes and electrons in the two directions. This is very efficient from this point of view. And then, in a normal, and you put a ferromagnet. This is LSMO, is an oxide of manganese that is ferromagnetic, and then inject spins. And also here cobalt is another magnet. This is a soft magnet, this is a hard magnet that you need in a spin valve. Then in this configuration, you make a kind of system that is working as an OLED without any problem. You observe green light due to this polymer. And then now the problem is that you need to improve the interfaces, otherwise you have not light and you have not spin polarization. Then if you start with cobalt and LSMO without any kind of the interface with the organic or green, if you want green semiconductor, the energies are quite different, these energies. Then you cannot inject electrons or holes. You cannot inject electrons, you cannot inject holes. Here you cannot inject electrons through the LSMO or holes through the cobalt. For that you need to increase the energy of these work functions and to decrease the energy of this work function to match the two, to do the situation. Then for doing that, here we have introduced a monolayer of a molecule that is a dipolar molecule, and introducing a dipole at the interface, this dipolar molecule increases strongly the work function of the LSMO, or increases from the point of view of the energy, if you want. Okay? For the point of view of the value, is decreases. But well, you understand. Then you have this kind of situation here, and then with cobalt you do the same. If you don't put anything, it's here, you put molybdenum oxide, it's decreasing now, and then you are in the good situation. Then you have done a system in which you have put LSMO, the cobalt, well, you cover with gold to avoid oxidation of cobalt, and in the middle you put here an interfacial layer and here another one, that are the two layers, the PEA or the molybdenum oxide. And in that case, you can inject electrons here, you can inject holes here in a very efficient fashion, and this system, for example, if you don't put this electron injection layer, you see, with an electron injection layer, in the case, you observe light also, but the light is at higher voltages, at 9 volts, at 20 Kelvin. But if you put this kind of PEA layer or another kind of injection layer, that is this one, it is also possible to put more layers, then you, at 7 volts, you have already light and one order of magnitude better. Then only by introducing a monolayer, a single layer of this kind of organic molecule that is a dipolar molecule, you improve by 1 order of magnitude the emission of light and you reduce the voltage. Then it's quite nice to see this small molecule, the strong effect is producing on the device. Then you have a very better performance having this kind of system in which we have improved as much as possible the interfaces. Then, and now we should check if we observe a spin polarized injection, if we observe a spin bulb. Then you can see here at 14 Kelvin, for example, then you observe the butterfly behavior I told you before. There is a spin bulb behavior in which you have high resistance when the two spins are anti-parallel, here and here, and low resistance when the two electrodes are parallel, magnetized is parallel. Then this is a spin bulb at 3 volts. At 5 volts is also a spin bulb, at 10 volts is also a spin bulb. Then we are able, thanks to this improvement of the engineering of the interfaces, to observe for the first time very high voltages, or for the first time these values. I mean, there are people that have observed 1 volt, but to observe 10 volts and to observe extreme magnetic resistance is not normal. And then it's thanks to this engineering, it's possible to do this kind of situation. And in this situation, okay, if you have this situation, at 7 volts, more or less, that you have also observed light, you can observe simultaneously light and, in that case, magnetic resistance. Then, if you focus at 10 volts, or 7 or 10 volts, if you want, at 32 Kelvin, you observe here, or here, you observe that there is, when the two electrons are anti-parallel, an increase of the light. The light increased here by 1%, but you can increase to 2%. Then it's not high value, it's not 50%, that is the maximum we can reach, but it's a proof of concept to show for the first time that it's possible to have this control of the luminescence thanks to the spin polarized injection of due to the magnetic electrodes. Then we have observed for the first time this kind of effect. Then we have an enhancement of the luminescence via this spin polarization. Then even if in this state is a state very resistive. I told you before that magnetic resistance here is bigger because the spins are the magnetization is anti-parallel and the spins that are injected are scattered in that case. Then, even if the current in this system is lower, you have much less current in this system, and then you should expect a reduction of the magnetic resistance of the light, or the emission of light, because the current is not flowing through the system so easily in this position. Even in this situation, you have an emission of light that is quite high, is higher. Then it's a kind of concept that in which I have shown you that it's possible to prepare multifunctional spintronic device through this interface engineering, in which by applying a magnetic field you can increase or decrease the intensity of light. Okay, then this is a result that is, well, it's a kind of applied result. Okay, then which time is now? Because it's...
We're about an hour.
Eh?
We've been here for about an hour now.
Okay, then I will show 5 minutes of that and I can stop. We don't need to continue much more. Okay, then now I have shown you that it's possible playing with molecules, putting molecules in this kind of devices in order to have these spinolets, these multifunctional devices. Now, the idea is to try to make molecular memories playing also with some spins, with some magnetic molecules. Then, this is people that are working on that is mainly Julien Dugay and Monica Jimenez. Then, in this case, the materials that we are using is what we call spin crossover nanoparticles. Spin crossover, I will show you what is that. And then, the molecular devices we are going to show are molecular devices that allows you to manipulate and detect this molecular spin. Then this spin crossover molecules has a molecular spin, and then it's not easy to detect if the spin is low spin or high spin in a device, because the spin is a property very weak. Well, you have electrons traveling, the transport you can measure very easily in a system. But to detect the spin is very difficult in a system. You detect the spin in an indirect fashion. And then, which are these kind of molecules? The molecules that we are going to talk are molecules that you see is simply, from the physical point of view, is simply an iron 2 molecule that is in an octahedral coordination, independent of what you put here, in which, thanks to this octahedral coordination, you have iron 2 is a D6 system, can be or in a low spin configuration or in a high spin configuration. Then, if you are in a system in such a case that the crystal field is weak enough to have this kind of equilibrium between this state and this state, you will have a spin transition when you heat your system. You pass from low temperatures to high temperatures, you can pass from this state to this state. Or when you apply light. Applying light also you can excite your system, you pass also to this state. Or by pressure. If you are by pressure, the system has higher volume, the volume of this one is higher than this one, you apply pressure and then you favor this one. Then it's a kind of by stability in your system. You can pass from one to the other, playing with light, temperature, or pressure. Then, okay, but you have two states. You have a state with a spin 0 and a state with a spin 2. And then the idea is to try to detect these spins through a device, through an electronic device. Then, okay, first we should construct the system in a nanometric fashion. A single molecule is too small for putting contacts in a reproducible way. Then we choose nanoparticles. Nanoparticles that you can make of this material. This is a chain material. It's not so important, but the nanoparticles are of more or less is 10 nanometers nanoparticles. Then these nanoparticles, you can measure the magnetic properties of these nanoparticles, and this is the magnetic properties. The system, this is the magnetization of the system, and this is the temperature. The temperature, if you increase the temperature, then the system is at low magnetic magnetization state, and then above 380 Kelvin, the system goes to a sharp high spin state, and after when you cool down, the system stays in a high spin state until you reach another temperature, 340 again, and go back again. Okay? Then you have this kind of biostability in which low spin and high spin coexist, for example, in 360 Kelvin. That is hot even for Valencia. Then it's not that every molecular system works only at low temperatures. It can also work at high temperatures, even to high temperatures in that case. Then this system, you can put a suspension of these nanoparticles in octane, for example, in a solvent, and you can see that at 80 degrees centigrade, that means here in the middle, the system can be in low spin, that is violet, and in higher spin, at the same time, that is colorless. Then you can have the two states at the same temperature. Then it's a situation of biostability. Then you can use that as memory, because the system has a magnetic or a thermal hysteresis, and then it's clearly a memory system. Then you can be in this state or this state, depending on way is your history. You can pass from one to the other easily. And then, okay, you can do that at temperatures that are too high here. Doing some chemistry, it's possible to shift this temperature to room temperature, 320 or 340, that is, well, more or less already is hot in summer, but it's more or less the temperature we have here. Then we can go, but you can go also to 300, that is possible also to 300, adding a little more of amino group, that is not so important here. But okay, but it's a little vary in the crystal field. It's only you vary the crystal field, and vary the crystal field, you can switch your system at room temperature. Then the important story is that with nanoparticles of 20 nanometers, you have this hysteresis. 12 nanometers, you have this hysteresis, and 4 nanometers, you have still hysteresis. Even with nanoparticles of 4 nanometers, you have memory. Then you see, 4 nanometers means nanoparticles with 20 atoms of iron. These are chains of iron. There are 4 chains here. 20 atoms of iron is enough for having hysteresis. There is a cooperative effect, but even with 20 atoms is enough. Then, okay, the idea is to try to take advantage of this biostability, and for that you should connect your system, your nanoparticle, to an electronic device. Then, for that, okay, we're working with Gerrit van der Zandt in Delft, and then in that case, this is a two-contact system. This is gold here, and gold here, and here there is a gap. Then the width of this is 100 nanometers. You can put here a single nanoparticle if you want. By some method, it's possible to put a single nanoparticle of your spin crossover. Then the nanoparticles are of the order of 10 nanometers. Then 5 nanometers gap, then you are sure that your nanoparticle, one nanoparticle will be in the middle, and then you can measure the transport properties. You measure transport properties, the IV curves. When you don't put anything, it's completely flat, there is no current through. But when you put a nanoparticle, you have some current. That means that the system, the molecule is having some transport of the electricity. It's having some conductance. Okay? Then this is at room temperature. Then now the idea is to see, because we expect that is in the low spin state and the high spin state, the conductance will be different, because the electronic structure is different for both systems. Then we did that at, we did the measurements at room temperature. We have this behavior, and when you increase the temperature at 325, for example, that increased by a value of 2.5 times bigger. Then that means that it's sensitive. You pass from low spin to high spin in this system, and if you plot the different values of different temperatures, not only 2 values, but you follow the process, you observe that you have between 300 and 350, for example, the system is in a low conductance state, and above 350, very quickly goes to a higher value, and then stays in this higher value, and after go down. Then you have here again your hysteresis for a single nanoparticle. Then this single nanoparticle is a memory that can be used to form one single nanoparticle. Okay, this is one possibility. Then and then you have this situation, and then it's also the first time that it's possible to show that a single nanoparticle is functional and show this kind of behavior. So this memory effect. Then okay, but this is a system that is too small to prepare, and then you can make a memory with that, but it's difficult to put all the contacts. One contact per molecule is not very practical. Then it's better to try to make systems in which you deposit a monolayer of nanoparticles instead of one, and then within that making two networks of molecular memories on graphene. Then we put on graphene, on a kind of graphene circuit, in which you have graphene here, you have silicon here, you have some contacts, some gates and everything, you have a kind of field effect transistor system in this case. Then we did that with Julian Dugay, that is now in Valencia. Then Julian, in that case, you can buy this kind of device, no problem. Then the possibility is, the idea is to put a monolayer of that and to see if the graphene is changing the transport properties when the state of the spin state changes. If the change in the spin state, the graphene is sensitive to that in the transport. Then we did that, and then we observed that yes, it's true. The system, if you study the properties of graphene near the Dirac point, in that case what you observe is that you have again the two values of resistance. Then you have a resistance here, when you hit, you have a resistance that is high resistance, and then you go to a low resistance state, you go here and you go up again. Then you can do this kind of system several times. Then in this case, the spin state that you have in your system is coupled with the electron system of the graphene. Then you can detect, in this way you can use the graphene as a sensor of the spin. Then you are sensing the spin thanks to the graphene. We have put a monolayer, but if you put a single nanoparticle or less nanoparticles, we have not studied which is the minimum amount of particles you need to put for sensing that, but it's quite nice to see how the graphene is sensing the properties of the spin that you are putting on the top, because the electronic configuration is changing, also the vibrations of the system is changing, and it's a question of, and also the the electric constant of the nanoparticles are changing. Then it seems that the electric constant of the nanoparticles are coupled with the phonons of the graphenes, and this is the reason why you observe this variation. But it's not the spin, it's not a coupling between the spin and the electrons. It's a coupling between in that case, the dielectric constant of your system, and in that case, more the vibrations in the graphene, the phonons in the graphene. Okay, but this is an idea also that is nice, because it's possible to use graphene as a sensor of the spin state, not only of the system, but in any system that you put in that you have this kind of variation in these properties. With graphene, we will observe the same result. Then it's a nice result. Okay, then the result is that, the conclusion is that the molecular spin can be thermally switched and electrically read out at the nanoscale. When you can read your spin at the nanoscale at room temperature. Then this is one system also that shows that it's possible to make, to study if you have a spin or you have no spin in a device, and to use this kind of system as memory device. Okay, then with that I think that I have finished. I don't need to continue more, because we have already more than 1 hour of talk, and then it's too much. Then the message is only that with molecules you can not only do chemistry, but also you can have some input in physics, in that case in solid state physics, and playing with electrical properties, conducting properties, magnetic properties of molecules, luminescent properties of the molecules. And this is a kind of message that is not so useful to use so far the molecules in some applications, but you have seen some molecules already used. For example, the OLEDs are already an application in the screens you are using. Soon you will see the OLEDs also for applications that can be also medical applications and other kind of applications. And The spin valves, also the Spintronics, is a kind of application that is not far from having molecules that also can be used for making OLEDs that can be better than the ones you have now, or making also systems, memories made by single molecules or by a small amount of molecules. Thank you very much.
Thank you. Thank you for this glimpse into a fascinating world. Few questions. Yes, traditionally the first question.
Okay, Eugenio, I have many questions, but I will concentrate in one, okay? One of the problems we have in particle physics, in elementary particle physics, is that in some occasions we want to change, to reverse the sign of the spin components of the particle. And we have only one mechanism, which is a master. You see, the mass is able to do that. But you understand that for high energy particles that normally we use, then this is essentially impossible. Then there are two possibilities. Either you say this is impossible, or you think more, okay? Then we think more. Then one possibility is what you do. When you want to reverse the sign, you implant the system into a crystal. You induce a barrier, and then use quantum tunneling in order to connect the two states. Is it true? Is this the method?
Well, the method, you see,
Implantation in the crystal.
even if you don't put in a crystal, if two states are degenerate, in that case they will. If
The interaction. You can call it interaction.
But these two states, if there is a mixture between the two states, even without crystal, you have also this kind of.
Yes, for example, in a semiconductor, you have a spin orbit splitting, things like that. That means there is an interaction. All external agent, interaction or whatever, then you have a barrier. Okay? And then you are able, quantum tunneling, to connect one state with the other. Later, you say, okay, but I'm interested in having a splitting of the two states, a gap. And then you put a magnetic field, a Zeeman effect, in order to have the splitting. My claim is that you don't need the Zeeman effect and the magnetic field.
No.
In any situation in which you have quantum tunneling between the two states, the stationary states of the system are no longer the original ones. It's like ammonia molecule, okay? Just for talking about molecular physics, ammonia, okay? Then the stationary states, the quantum stationary states, are not degenerate anymore. And you have a gap between the two.
It depends on the structure of the
Why
system.
you need the magnetic field in that?
No, we need a magnetic field because when you apply a magnetic field, is just the moment, by applying a magnetic field, you are approaching, instead of separating the system by a Zeeman effect, when you apply a magnetic field, you are approaching. Then you are doing the reverse. With a magnetic field, you are approaching the two states.
You want to decrease the gap.
Yeah.
In order to have a crossing.
Yeah, you approach the crossing regions, and then it's the crossing regions in which the Zeeman effect is zero, because in that case you have not a slope in your functions. Then, but you see, if you don't apply a magnetic field, okay, you have a resonant tunneling, and then this is the best one for having the localization. But this one, is having this kind of resonant tunneling results in a gap, but the gap is due to the mix of two functions, like in hydrogen molecule. You have hydrogen molecule, two orbitals that interact, and you have a bonding and anti-bonding state. Here is the same. You have two functions that mix, and you create two new functions, one at zero field, one with low energy and one with high energy. This tunneling gap indicates only that your functions are strongly mixed.
Okay.
But you have a strong mixture, and after, in some cases, your system with these functions in this way are in such a way that the electronics structure, you have some crossings of levels, and in these crossings of levels is when we focus we put the magnetic field to approach to these crossing levels, and in these crossing levels the system is insensitive to the magnetic field. But you need to apply, in that case, a magnetic field for having the crossing of levels.
Okay, thank you very much. And now only a general comment. in this field there is a lot of change in the wording. What in the old times was an individual molecule now becomes a nanoparticle.
No.
But in the old times was, you see, hysteresis now is called memory. Okay, but the phenomenon...
We use the same terms.
phenomenon
I use molecule when it's molecule, and when it's a nanoparticle, I use nanoparticle. Nanoparticle is not molecule. Nanoparticle is an ensemble of 20 or 30 molecules.
okay.
Because a nanoparticle is the object is a nanoparticle.
Yeah.
And also, I use...
At the microscopic level, not at the level of the global material.
No, but the wording is... I use hysteresis, and I use also that when you have hysteresis, you can have memory. The consequence of hysteresis is the memory. It's not that I use memory and hysteresis the two in different ways.
Further questions? Herman?
For a particle physicist, a spin larger than 1 or 2 is too much. So, just for curiosity, what is the largest spin molecule with the largest spin that you know, and whether it is advantageous to have molecules with a larger spin, or it's better to have lower spins?
Well, molecules, the highest spin molecules that you can find is of the order of 50. Spin equal 50. That means 100 electrons all with the same spin. Then it's possible to have 50 as well. The problem is you have a very big spin, the other thing that is the anisotropy is also decreasing. Then the parameter of anisotropy is decreasing with the spin. Then in theory it's possible to demonstrate that there is a correlation between the increase in the spin and the reduction of the D parameter. Then even if you increase a lot the spin, you are not increasing a lot the anisotropy. Then you need the product spin multiplied by anisotropy that gives rise to the gap that you need, the barrier. Then even if you have a very high spin molecule, the barrier will not increase. Then you should look for another kind of method to have an increase for having, in that case, molecules with strong barriers, with large barriers. Then, but not 10 years ago, the people start to chemically to try to increase the spin state of the molecule in order to think that, okay, if the D is constant, more or less, I will increase step by step my gap and my barrier. But at the end, it was possible to demonstrate that D is connected with the spin, and in that case, D and spin the two functions are connected, and one is increasing, diverging, and the other is diverging but in the opposite direction. At the end, they compensate, and you cannot have higher barriers.
How far is what you do to applications? For instance, we heard that the famous giant magnetic resonance took 10 to 20 years to be applied to hard disk. What you do is, let's say, 10 years away from a real application?
Well, it depends of which kind of systems. There are systems that you can have applications already. That means the systems that can have applications already that are closer to applications in this field are at this moment, the OLEDs have already applications. Then in that case, for example, Henk Bolin, that came from Holland working in OLEDs or in Philips all his life, he has been here, he has been in interaction with some companies. Well, and then now he has changed because OLEDs is not longer for basic research. You can make OLEDs very easily that are very competitive. Then he cannot compete with other people. Then now, what is competitive is the solar cells. Then people are now doing, you have seen in the journals, the perovskite solar cells. Then with perovskites, now you obtain the same kind of, more or less, of efficiency, 20% like or higher than in the case of silicon. But the advantage is that these kind of systems that are not silicon solar cells are much cheaper to prepare. But and with less material, then the silicon is much more expensive. Well, the silicon is still competitive because the price of silicon is decreasing all the time. Then the price of silicon in 20 years has decreased by 1 order of magnitude minimum. Then you have this situation. But this kind of devices are competing with silicon or are complementing silicon, because if you have a silicon solar cell and on the top of the silicon solar cell you add a tandem, you add a second solar cell made with perovskites, the efficiency increases to 30–40%. Then you can have a much more efficiency in the silicon device. Then, as all the technology is based on the silicon, it's much more easy to do that than to try to compete independently from silicon. Then people now are trying to make these tandem solar cells, and then soon also, I have not shown that today, but soon this kind of tandem solar cell that will be made by us and by other people in Europe, because Europe is quite competitive on that, will produce already for the market this kind of device. That means in 10 years should be already in the market, this kind of system. The system with Spintronics is far away, because Spintronics started as a field, the molecular one, 10 years ago, then making some kind of, if you want, some of experiments, but were not for application, but only to understand the physics that is behind this kind of systems. But now, little by little, people are improving the things, and the Spintronics, for me, I suppose that will be still, you need more than 20 years more to have some application that will be real in the Spintronics part, because the Spintronics is always working at low temperatures. You have seen, I have shown you the spin OLED. Spin OLED is working at 30 Kelvin. You are not using a spin OLED working at 30 Kelvin. You have more light at 30 Kelvin, then nobody cares of having light at 30 Kelvin. But it's good from the fundamental point of view to prove that you have a spin injection on a semiconductor, that is an open problem. Then, so far, people has not proved that you have a spin injection in the middle, because you can have the spin bulb behavior without having a spin injection. The spin bulb behavior can be due to other phenomena that are not due to the spin injection. Then, in this case, if you observe light, it's because you have injected spins in a controlled way, and that's why you observe light, and you increase the amount of light. Then this is the first proof that you are able to inject spins inside. Then from the fundamental point of view, it's quite important. From the application point of view, it's not interesting.
Any further questions? Now, make the last one. We think, right, everyone knows quantum computing is going to be the big revolution. I can see how you can make a single memory cell or a single bit with molecules. You've shown examples there. And how can you make a whole network and address each of these individual cells? How can you scale that from a single cell to a large scale?
Well, it's a good question for solving. There are, first, the idea is to try to have in a single molecule several qubits together. Then you can put, for example, here we have a qubit, because in a system in which you have a doublet, the spin is a qubit. But you can have systems in which, for example, manganese 12, that is spin equal 10. Then you have several, if you in this system, you have several states, plus minus 10, plus minus 9, then each one of them can be a qubit. Then, and then you can play with microwaves, with the EPR, for example. You can address, you can connect this kind of doublets. And connect this kind of doublets means to make operations in your system. And you can have, instead of having one qubit, you can have in the same molecule, you can have 5 or 6 qubits. Then having intrinsically in the same molecule several qubits is quite nice, because with 6 qubits you can already do some computing. Then we have published a paper last month in Physical Review, in which we have demonstrated that we can have with one single molecule 3 qubits. It's the same molecule I have shown you here, but with gadolinium. It has a spin 7 halves. Then you can have also the splitting of the spin 7 halves, and then in that case you can have a 3 qubits, and you can make a quantum processor with 3 systems. Then you see, making this kind of tricks, you can have the advantage of the molecule, and then you don't increase the decoherence, because everything happens inside the same atom. And in that case, inside the same atom, you cannot decoherence. You have decoherence when you have dipolar interactions between different molecules, but in the same molecule, you have no decoherence if the atom is the same, in the same atom. And this is the way. The problem with that, always, to increase this kind of thing, is that you should, for reading out your spins, or for what you are doing there, you should connect your system, your molecule, or any kind of system, to a kind of resonator, to increase the signal, a superconducting resonator or whatever. Then you connect, and then this connection to the resonator is one thing that is the second step. Now people are showing in crystal that it's possible to do that. After, they will go to single molecules, and they will attach to resonators. Then now we are in the step in which In the resonators, in some resonators, we should maximize the interaction between the resonator and the molecule for having a signal, and this signal will be the signal that will be produced by the qubit or by the Q gate or whatever. But this step is a step that so far only the first trials have done. Then you see, that we are far away from being able to have, using the molecules, this kind of system, this kind of quantum computer. But there is also already a quantum computer exists in the States. In the States, they have also already constructed a quantum computer, but it's not probably with magnetic stuff. It's perhaps used with superconducting stuff or with another kind of approach, because with superconductors it's much more coherent. Then in that case, people are using several approaches to make the quantum computer. In Europe, they are trying to compete with the States. That's why they have put this kind of flagship. But so far, well, we are in Europe, people have been too slow in comparison with the States. The States, they have finished already to solve.
Behind the States? We're behind the States?
Yeah, we are behind because the States have already shown, you enter internet, quantum computer, you will see that there is a quantum computer that is working with, I don't know, with how many qubits at the same time, 20, 30, but it's possible to put a lot of, to make operations and to make the system to work.
Thank you. I think we stop here. Speaker again.